Welcome back, everybody. This is our video solution to problem 2 from quiz 6, and we're pivoting over to the definition of the Laplace transform. So this was a problem that on the exam people struggled with quite a bit, often overthinking it a little bit. So remember, the key here is we actually have to use the definition, and we have to use it literally. So let's start by writing down the definition. The Laplace transform of f is going to be the integral from 0 to infinity. And again, we'll pause there and note it starts at 0. Anything that happens before 0, the Laplace transform doesn't care about. So even though this function is defined across the entire real number line, we only care about what happens once we get to 0. So this infinity is not even the right thing to be thinking about, right? We should be thinking about a 0 here. So then I would take this function and multiply it by the decaying exponential e to the negative st. Now, because this is a piecewise defined function, it's not going to be convenient to integrate this all at once. Instead, I want to break this up over the 3 separate intervals. So I can go from 0 to 3, and on that interval, my f of t isn't just some random f of t, it's actually this very specific t minus 4. So I'll have t minus 4 e to the negative st. Then I can integrate from 3 all the way to pi. Oh, yes, a whole 0.14 and change. Yes, all the way. And then what is my function? Well, actually, on that interval, it's just 0. That's going to be the easiest integral of all, right? Doesn't matter what I write up here because this entire thing is going to be 0. I'm integrating, right, the 0 function. And then finally, I can integrate from pi to infinity. So I'll get an honest to goodness improper integral. And, ooh, the integrand's going to be rough. Sine of t e to the negative st. So I really have here 3 integrals, one of which is just 0. So I'm not going to worry about that. But now I have these 2 separate integrals that I need to compute. Both of them, of course, I'm going to use integration by parts. That's just what you do when you're using the Laplace transform. So let's compute these things individually, right? So if I integrate from 0 to 3, t minus 4 e to the negative st dt, again, I want to use integration by parts. Let me give a name to this integrand. Let me call this g of t. In fact, let me call it g prime of t, so that it's easier to use the fundamental theorem on. And if I want to compute an antiderivative for g prime, I'm going to use my tabular method, and I'm going to break it up as with my u as the polynomial piece and my dv as the exponential. So I take a derivative, I get 1, take another derivative, I get 0. Here I'll take antiderivatives, that's going to be negative 1 over s, e to the negative st, how annoying. Take another antiderivative, I'm going to get positive 1 over s squared, e to the negative st. Now I connect with my lines, plus and minus. And so my g of t, my antiderivative, is going to be, well, let's see, e to the negative st, that shows up in both. So I can pull that out. Also notice this one is going to have a minus sign, this one's going to have a minus sign, so I'll pull the minus sign out as well. And what's left over? I have t minus 4 over s, and then 1 over s squared. Okay, and so by the fundamental theorem of calculus, the second one to be precise, this is going to be g of 3 minus g of 0. Okay, that's not too bad. At 3, I get negative e to the negative 3s times, okay, 3 minus 4 is negative 1. So we get negative 1 over s plus, oh, just 1 over s squared. Okay, so this is my g of 3. Okay, then I do minus, okay, and now I need to do g of 0. So at 0, I'm going to get just e to the 0, which is 1. And of course, there's still a minus out here. So minus 1 times, okay, at 0, I have negative 4 over s plus 1 over s squared. Okay, and we could probably simplify this a little bit. Let's see. First, this negative hits this negative, and so this whole thing here is just going to be plus 4 over s plus 1 over s squared. Okay, well, there's not a whole lot I guess I'm going to be able to do with this. So what do I have? I have 4 over s, 1 over s squared, minus e to the negative 3s, negative 1 over s plus 1 over s squared. Okay, so that gives me the answer, right, to this leftmost integral. All right, now we want to get the answer to this rightmost integral. Well, here we go. So we're going to integrate from pi to infinity sine of t e to the negative st dt. All right, once again, I want to use integration by parts. Let me give a name to this. This will be h prime of t. And let's see. Well, I have a trig function and an exponential, and well, I think if you use that old LIATE rule, they would tell you that you should make the trig function, the thing you differentiate, that should be your u, and the exponential your dv. But I know from experience that I can do it either way, and I want to make the exponential my u. That way I'm not dividing by this negative s that's going to pop out. I can multiply by it. That'll make me feel a lot better. So I'm going to go e to the negative st on the left, sine of t on the right. You can't stop me. So I take a derivative. I get negative s e to the negative st, right? Chain rule's so much easier. An antiderivative of sine is negative cosine. I do it again. I'm going to get s squared e to the negative st, and an antiderivative of negative cosine is negative sine. Now at this point, other than this s squared and this minus, I'm essentially gotten back the original problem, right? So this tells me I'm probably in the I trick situation. All right, so if I let I equal an antiderivative for sine of t e to the negative st dt, then here's what I can do. I go into a box. I'm going to take the negative and the s squared and leave those on the left, and then I'll have sine of t times the decaying exponential on the right. So when I take a derivative on the left, I get 0, and on the right, I'm just getting an antiderivative, which is just I again. Okay, so I draw my lines, remember, never inside the box, plus, minus, plus. And so we get I is equal to, well, let's see. Each one of these is going to have, well, actually not the last one, but the first two is going to have an exponential. So let me pull that exponential, and then there's a minus, 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 minus is another minus. So I can pull a minus out, and what's left over? I have a cosine of t. Then I have an s times sine of t. Okay, but then there's this extra bit at the end, which is the minus s squared times I, right? And that's what's going to combine with the I on the left, right? That's the so-called I trick. So I'm going to add s squared I to both sides. So, and when I do that, of course, I'll be able to factor out the I, and I'll have s squared plus 1 of them. And that will equal negative e to the negative st times the quantity cosine of t plus s sine of t. Okay, I can divide by s squared plus 1. And I'll have now found my antiderivative. So I'm going to end up with here negative e to the negative st times cosine of t plus s sine of t, all divided by s squared plus 1. Right? That's my I, or if I like, that's my h, right? So this is actually my h of t. Okay. So in order to compute this, I now have to evaluate h at infinity. And remember, that really means I'm taking the limit as t goes to an infinity of h, minus h of pi. All right, well, first thing, we're right into the fire here. We have to look at what happens, right, as t goes to infinity. So what is the limit as t goes to infinity of h of t? Well, look at what we have. On the bottom, there's no t at all. That's just some constant, so that's not going to worry us. I have a decaying exponential, Ooh, we know those go to 0 very fast. Okay, what else do we have? Well, we have cosine of t. Now, cosine is just going to oscillate between -1 and 1. Sine of t is going to oscillate between -1 and 1. Okay, you multiply it by s, and it'll oscillate between -s and s. But in any case, these things are bounded, right, above and below. And then you're hitting it with a decaying exponential. So this is going to converge to 0. If we want to do this precisely, right, we can do the following. You can say, well, cosine of t is bounded by -1 and 1. And sine of t, that's bounded by -1 and 1. And if I put an s in here, and of course we can assume s is positive, then this is going to be bounded by -s and s. And so if I add these together, I get -1 minus s is less than or equal to cosine of t plus s sine of t. And that's less than or equal to 1 plus s. Okay, but then what's happening when I multiply by this decaying exponential? All right, so if I hit it, forget about this negative for a moment. I'm just going to multiply by the decaying exponential. E to the negative st times -1 minus s will be less than or equal to e to the negative st times the cosine of t plus s times the sine of t will be less than or equal to, again, I multiply by the decaying exponential. And on the left and the right, I don't have to worry about the cosines, right? I just have a decaying exponential times a constant. And this guy on the left converges to 0. This guy on the right converges to 0 because you have a decaying exponential. And so by the squeeze theorem, squeeze it together, this bit in the middle converges to 0. And then putting a negative isn't going to change that. All right, so this limit is actually 0, and so h of infinity is just 0. Okay, what about this minus h of pi? Well, if we let t equal pi, we're going to get negative e to the negative pi s times, okay, the cosine of pi. Cosine of pi is -1. And s times the sine of pi. Oh, sine of pi is 0. So this is just s times 0. Nice. Divided by s squared plus 1. Okay, negative and a negative is a positive. And then, oh, wait, I have another negative. So we get negative e to the negative pi s over s squared plus 1. All right, so we could recopy all these things, right? We could take this guy over here and make a little copy of it and put it up here. Make it a little smaller so it matches up. Hey. And we could we'll just do it by memory here, right? We had negative e to the negative pi s over s squared plus 1. Okay, that'll be that last bit. And of course, the sum of these is going to give you your Laplace transform.